In this video, we will take a look at new features and plans for the OpenFFBoard project. Since the last update video, most of the changes were on the software side. Some more visible and some more in the background to simplify development in the future. The internal command system was rewritten almost completely to suit the internal class structure better and allow easier development of internal functions and external computer-side programs via HID and CDC, and possibly even UART to change settings, for example with Arduinos, to add a physical configuration interface to your simulator. First, I would like to take a look at support for new motor drivers like these you can see here on my desk. We have support for the ODrive, which is kind of similar to our TMC, the VESC, and I have also made a new prototype version of a slightly optimized TMC with Hall sensors, which we will take a look at later as well. These motor drivers, the VESC and ODrive, communicate via the CAN bus. We have a CAN transceiver on board on our FFBoard. This is this small chip here in the corner. And these are the first two functions to use this CAN transceiver as well. And it's quite simple to add support for new motor drivers using the CAN bus in the future as well. You have to take care that the CAN termination resistor, which is here next to the CAN transceiver, is actually connected to the CAN high and CAN low lines, because a CAN bus needs to be terminated with 120 ohms at both ends. So because the ODrive actually contains two motor drivers, I would have liked to show you a 2-axis joystick setup with two motors, but yeah, this is mechanically pretty complicated and would be something for its own project video. So we will just quickly set up a little force reflex steering wheel with this motor and check the basics, how to set up the ODrive, but we will not go in depth of really how to tune the ODrive and set everything up for this motor. This depends on your motor and encoder, and we are concentrating on how to send torque to the ODrive actually. Right now the ODrive is not turned on, so we need to enable it first. So we turn on the power supply. Now you can see we have a connection. And the first time the ODrive turns on, the FFBoard will cause the ODrive to enter a full encoder calibration sequence if it's not already in closed loop control mode. And now it is already sending torque. But for this to work, of course, we need the communication. So the most important thing is to first set up the CAN speed and the CAN access ID. So the CAN speed is sent in the ODrive tool, in this case to 1000K. And also in the FFBoard, I would recommend either using 500K or 1000K, because we need to read the encoder position and update the torque with 1 kHz, and 250K is just barely enough for that, and any issues on the bus could cause problems and possibly congestion and packet loss. And for 2-axis, this is even worse. For 2-axis, I would always recommend 1M. Then we of course also need to set the node ID, because this is the M1 channel of the ODrive where the motor is currently connected. We need to check the axis 1 in the ODrive tool, and this is currently set to node ID 1. And this is also set in the config tool. For axis 0, we would have the default value of 0. Or if you have changed it, well, you need to set it in both the ODrive and the config tool as well. So we can also read the input torque, because this is basically what the FFBoard is sending. It will just send continuous torque values to the ODrive. What the ODrive does with it, I mean, it depends on the ODrive configuration, and this is not part of the FFBoard. So if we turn the wheel and read the input torque, you can see it changing. And this is a float value in Newton meters. This means we need to know the maximum range of the motor, because we can't just send an infinite number of Newton meters. This would, of course, clip, and the ODrive wouldn't be able to reach that. So for that, we have the max torque range, which is currently set to 3 Newton meters. So this means if a game sends the maximum possible torque and the power slider for scaling is also set to the maximum, then this will correspond to 3 Newton meters, and 3 Newton meters will be sent to the ODrive. Checking the input torque is also a good way to debug any issues. If you don't have, for example, any force, but want to see if the FFBoard is actually sending torque, then you can read the input torque value on the ODrive directly. Normally, the ODrive will also have some safety mechanisms in place, like the overspeed error. This is something you absolutely need to disable if you want to build a steering wheel, because otherwise either the wheel will turn too slowly because it's speed limited, or if it's not speed limited by the ODrive, it will cause the overspeed error to shut the ODrive completely down, and you won't know why it just suddenly doesn't have any force anymore. I have now connected a VESC to a battery and our FFBoard with the CAN bus connection. The encoder is also connected to the VESC. And yeah, you have to take care to use a battery or a brake resistor circuit, which you have to design yourself, because unlike the ODrive and also the TMC, the VESC is made to be powered by a battery and doesn't have a braking resistor and protection diode for the power supply. If you were to connect a power supply to the VESC and turn the motor, then this would feed back power into the power supply and very likely trip the overvoltage protection of the power supply or even damage it. I will not show you the whole setup procedure right now, and just a short demo. We can do the setup in another video. I assume you already know how to set up the VESC and the FFBoard. So yeah, I have connected the VESC and selected it as a motor driver. The CAN speed is set to 500K, and also in the VESC ID must match, or it has to be 255, which is the broadcast. And use VESC encoder should be checked as well if you don't have a second encoder connected to the FFBoard. If everything is going correctly, you should see the information update, and it should be sending torque as well. Of course, during the setup in the VESC tool for the motor, you should absolutely disconnect the FFBoard so it doesn't send any torque, and it can do the whole calibration sequence correctly without anything interrupting it or causing a dangerous situation. And if you have also checked the use VESC encoder, then you will be able to use the VESC encoder via CAN bus as a gamepad access. Otherwise, you can also combine it with an external encoder connected to the FFBoard directly and use the VESC completely on its own just for taking torque and controlling the motor. Now, normal force feedback effects are of course also working. I have enabled the spring effect in the iRacing force feedback test tool. And when we move the rotor shaft, then we can see the current rising in the VESC tool. And when we enable the sign, then it will also move on its own. I have now connected the MT encoder on the servo motor via SPI to the FFBoard and with its ABN output to the VESC. This is basically just like having two completely separate encoders, one connected to the FFBoard and one to the VESC. And the use VESC encoder checkbox is not checked right now. And as the encoder source, not the VESC is used, but we have selected the MT encoder via SPI3. And it is still completely working normally. Of course, in this case, you have to make absolutely sure that the direction of the motor force and the encoder matches. Otherwise, you would have an inverted force and the motor would just run away. And to demonstrate that it is actually completely separate encoder systems, I can disable the VESC by setting the motor driver to the none motor driver, which does basically nothing. And we can see the force is disabled and the encoder is still updating. And we can go even further. We can completely disconnect the VESC, the encoder connection to the VESC, and also the CAN bus. Now the VESC is completely disconnected from the FFBoard, and our encoder is still updating. The feature of combining FFBoard encoders and motor driver encoders is something which is also planned for the TMC, but this is something we are currently working on and it might still take some time. Regarding the TMC4671 based motor driver I am developing specifically for force feedback in this project, there was not a lot to do in the last months because parts are still very difficult to get, but I was able to make at least one new iteration of this hardware. The last and the previous versions used the analog devices AD8417, which you can see here, this chip. And this one provides pretty much excellent PWM rejection for a shunt amplifier, but it still is a very sensitive part that can be easily damaged during assembly or when misused from overvoltage, for example. In search for a better alternative with possibly even better noise rejection, I modified an old driver and made some breakout boards for different sensors to connect externally. I have tested some shunt-based solutions, but as we are dealing with high common mode voltages of up to 60 volts, I also wanted to try out some Hall sensors. The best performing Hall sensors I could find for this application were the LEMGO 10 SME and the TI TMCS 1100A2. The LEM has very good external field rejection, but I was unfortunately only able to get enough samples from the manufacturer for my experiments. The TMCS does suffer from external noise and offsets from external magnetic fields a bit more, and even the orientation matters for this sensor, but otherwise it was also a solid candidate. So I have designed an updated version of the V1.2 board and replaced the shunts, amplifiers and filters with these Hall sensors. These are what you can see here. And on the underside there is nothing. Previously we had the shunt amplifiers on the underside. One of these uses the TMCS 1100A2 and one the LEMGO 10 SME, which is also the one I'm currently using most of the time right now. Also, as mentioned previously, the ADC inputs of the TMC do leak some current out and require a buffer driving them. So a quad op amp was added to the design as well, which is used for the temperature sensor and the voltage divider, making them more accurate. The third channel buffers the 2.5 volt reference, and the last channel was used as a comparator to activate the brake resistor at a fixed point if the software activation fails for additional redundancy. Unfortunately, a lot of parts became unavailable again for this version, so you see different MOSFETs on these boards, and I also had to find replacements for many other parts as well. And unfortunately, the LM74700 ideal diode controller used in the previous version also had to be replaced for these prototypes with a diode instead of the MOSFET. The pad of the LM74700 was left empty in this version. And I mean, the diode is also less efficient than a MOSFET, so I added a heatsink on this board as well. I wouldn't recommend using a diode instead of the LM74700, but because of this availability issue of so many parts, I have not released the files for this version yet, and even if I do, please keep in mind that you may not be able to buy some of the parts, or that they were already replaced by me, and you may need to find some alternatives yourself. Overall, the reliability of this version should be better than the shunt-based version, but the performance of those new drivers is pretty much similar, and it was more an experiment to see if we can even use these Hall sensors than a full-on new and improved version. So in the end, the LEM Go is more stable than the TMCS, so that's what I am using most of the time at the moment, but the TMCS is still very usable if you keep in mind that it is affected by external fields a lot more. Now let's take a look at the new command system for configuring your system at runtime. This is what the configurator uses to change values inside the firmware. The internal command system was rewritten almost completely to better fit the modular class structure of the firmware. Previously, in the old system, a command would be passed into its base command string, like for example power, and a value which would then be passed to all the classes inside the firmware until a match was found. This is of course quite inefficient, and you have to be careful to never have two commands with the same name in the whole system. The new system addresses a class directly via its class name, an instance number, and a command name, and also a type if you want to read or write a value or get some kind of information from it. This allows you to have the same command in multiple instances or classes. For example, if you have multiple encoders, you don't have to prefix the command itself with the name of this class. Each command and class also have an ID associated with them, which can be used the same way as the string names in non-string command interfaces like HID reports, which we will also take a look at. So in the code, each class has its ID 0xA02 for the fx and the name fx. It also registers at startup its own commands, like spring with the ID 3, which is the spring gain, which you can also see in the wiki page. And there are also some internal commands, which pretty much every class has. This is also a reason why we had to address classes instead of just checking command names. This way, by registering the commands at creation of the class, you can also add a help string. And by the way, we also have highlighted now the FFBoard devices which are compatible. So if I type fx.help, I get the help message of the fx class and all of its commands with the corresponding help messages. Now let's take a look at how this works internally by using just a normal terminal and requesting the ID of the main class and also its name. So we can use the system class sys.0, which is always 0, and we type main ? And we will get back a start marker sys.0.main ? a separator, and the value, which is 1. This corresponds to the index of the force feedback wheel class, and then we get a new line character. So this makes it easy to also parse in the software multiple commands chained together, and it also knows to which command a reply corresponds. And we can also get the name of the main class. Each main class is called main and always 0, but we don't actually need this 0. This is optional. If you don't specify it, it is always 0. And we get the name. And this prints back force feedback wheel. And to get a list of the system commands, for example, you can just type help. And if you use the config tool and you just type help, it also prints a formatted list of the system commands and also of the available classes, which can also be read by the ls-active command, or also in the active features window in the head drop-down menu. And for example, if we activate more functions and refresh this, then we get more in this list. Here, for example, you can see most have the instance number 0 because we only have one of them active, but a special case of the ODrive, it is instance number 1 because we have selected the ODrive M1. There's the ODrive M0 and M1, which are the two motor drivers internally in the ODrive. And the M0 is the first motor driver, which would have the instance number 0, and the M1 has the instance number 1. Now, because every command also has an ID associated with it, we can use this for interfaces which do not allow sending of strings, like for example HID reports. So we have created a HID report for these commands, which is active when the force feedback wheel main class is loaded. And it contains a type, which is either read or request a value, the class ID again, and the instance number, which is the same thing as in the CDC protocol, the command name, which is the command ID, which is listed in the ID column. And then we have two data fields, data and address, for reading or writing a value. Most commands just use one, but in some cases you might need two values. For example, if you want to send a CAN packet to a specific address, for example. To test the HID system, I have created a small demo script in Python, and we want to get the power value from the axis, set the value to 500, and then get the power value again. This calls a small wrapper function, which makes it a little bit easier to create this packet. So now we will also open our configurator and go into the Access tab. And now we see the power value is 5534. And when we run our script, then you see it has printed out the power value, set it to 500. At the same time, the slider also updated in our configurator, because on some interfaces, like for example on the CDC and HID ports, it will broadcast changes in values the same way like they were read by this interface. Access.0.power. And I can do this again, and as you can see, it sent the same reply, just automatically. And the same thing also happens the other way around. When I change the power slider, it will also broadcast the change on the HID interface. In this case, the power slider is throttled a bit because it is so high resolution, so we don't flood the HID system. This can be very handy because with HID you are not blocking the serial port. So with the serial port only one program can be connected to it, but HID is broadcasting. So this is perfect for third-party applications which want to automate some settings. One example is the Assetto Corsa Content Manager. I have modified a version and added support for the hardware lock for our OpenFFBoard as well. This is at this time not official yet, but I just want to show you that this works. So I have created an additional script for the content manager, which creates the HID packet with the angle command for the axis, and then it will automatically change the steering wheel angle depending on the car you are driving. And just quickly to show it working, let's take a look at our range slider while I am joining a race. And immediately it set the angle to 640. And when I abort, the range was changed back to 900 again. Another information which might be interesting for developers is that we now have a Doxygen site. And here you can navigate all the classes and source files. And it also automatically generated these class hierarchy diagrams. So, for example, we can go into the ODrive, which is a motor driver and an encoder and command handler, and has the ODrive CAN1 and CAN2 instances. And for some of the functions, there are also comments in Doxygen syntax. Not for all of them, but as the time goes on, I am trying to write more of them so that this page can be used as a reference as well. And it might already be quite interesting to check out the source code and quickly jump between different classes and get an idea of how the layout of the firmware works. If you are still watching, you might want to check out the links in the description for more information about this project. And also huge thanks to all my supporters on Patreon, everyone contributing to this project directly, and all members of our Discord community, where I post more frequent updates, answer your questions, and plan to do more live events as well. You can find the Discord also linked in the description and on the project pages.